transcripts of the talk. And if you are in the room, we recommend that you turn off Zoom because it will have better sound quality. So I'm happy to introduce as a first speaker Tadahisa Funaki from the University of Tokyo, and he will talk about motion by mean curvature from interacting particle systems.
Thank you very much for kind introduction, and I thank the organizers for inviting me to this workshop. I really miss to visit Newton Institute in person. Still, it's a big challenge for me to travel from Tokyo. Sorry, I feel very sorry about that. And also, I thank the organizer for giving me a little longer time. So that means I have to explain some background, the hydrodynamic limit. So this is a joint work with Sundar Sesuraman, Daniel Gilhorst, and also Hyunji Park, and also Pera Kettani, and also Tsunoda, Kenkichi Tsunoda, and Patrick Van Mars. So it's consists of the 4 papers, which I will show you later, still on the archive. So I want to, before starting my talk, I want to explain some background and some history of the hydrodynamic limit in the probability group. That was asked actually by the organizer. So hydrodynamic limit for a probabilistic model means we have some microscopic dynamics, which is a large-scale interacting systems with stochastic mechanism. We usually consider on the discrete space or the continuous space. Then under some scaling limit, we derive macroscopic nonlinear PDs on the continuous space. And this scaling limit means the space-time scaling limit, but especially it has a very special character, so-called the local equilibrium, and also averaging under the local ergodicity. And this is quite important for the hydrodynamic limit. Because if you remind the derivation of the hydrodynamic equations from Boltzmann equations, say, we pass by the Maxwellian distribution. It is known that by Hilbert expansion or the Chapman-Enskog expansion, for which the mean-free path becomes very small, then always it passes by the Maxwellian distributions. Maxwellian distribution is a Gaussian distribution, but it is an equilibrium measure in the velocity fields. But Maxwellian distribution is characterized, say, the mean and also variance, and also its magnitude. That means the Maxwellian distribution changes in the macroscopic space and time variables. This is the local equilibrium, actually. This is the local equilibrium. So this structure is very important to discuss the hydrodynamic limit. And also just recall that the Boltzmann equation itself was derived from the microscopic particle system, in his case, just Newton mechanism, but under the ergodic hypothesis. So in a sense, we need the ergodicity to derive the hydrodynamic equation. But in the probability group, we usually add some stochastic mechanisms. This makes it easier to prove the ergodicity or the local equilibrium. So, okay, so I just give a very simple example, which is the independent case. The first is a continuous case. Actually, this was first discussed by Dobrushin with Zygmunt Schultz a long time ago. So they discussed more some Markov processes, but for simplicity, let's consider independent Brownian particles, and then these are independent objects. Then we certainly have some law of large numbers. And if we consider empirical measure of the, so Brownian motion, Brownian particles are microscopic object. Therefore, we introduce a space change. So we divide it by n. N goes to infinity. Therefore, space magnitude is anyway squeezed by n. At the same time, we consider long time behavior. Therefore, this is the diffusive scaling acting to the Brownian motion. And we put the mass at this point, after scaling, we put the mass 1, but we divide by n to the power d. This means each Brownian motion has the mass 1 over n to the d. So originally, each Brownian motion has a Brownian particle has a mass 1, but we introduce the scaling. So this is microscopic object, but after this space and time and also mass change, we go to the macroscopic level. Then by low large number, actually it is not, so we call this empirical measure or the macroscopic empirical measure. And it's not so difficult to show that this converges, this object converges to the some measure with the density rho Tx, and the rho Tx satisfies a heat equation. However, under this limit theorem, actually we have a Poisson random fields, and we call the Poisson random field on Rn with a density rho by new rho. Then, depending on the macroscopic time t and macroscopic position x, we have a picture that this Poisson random field changes, but around this point tx, its density is actually rho tx, and the density, the evolution of the density followed this heat equation. In the independent interacting case discussed by Kondratiev and others, is one of the organizers of this meeting. And also, we discussed independent simple random walk case. We instead of B, we consider random walks. Then, yeah, the limits should be the same, because if you take a random walk, then by the invariance principle, it behaves almost a Brownian motion. Therefore, the limits should be the same. But for the independent simple random walk case, random walks move on the discrete space. And instead of the Poisson random field, we have a Poisson product measures on this discrete space. And later, we discuss not the independent case, but the interacting case, interacting random walks. Then instead of each motion of the random walk, we actually observe the number of the particles which occupy the site x. So later we will use this notation eta xt. That means at the position x, how many random walks occupies at this position x at the time t. Okay, then I give some short history. I don't know who was the first, but I once heard from Enrico Presutti that he gave a name of the hydrodynamic limit, starting from this paper with the Galvez and Kipnis and Marchioro. And because they are in their paper, they don't write clearly the hydrodynamic limit, but they found this kind of local equilibrium structure behind the particle systems. And also we will discuss the Boltzmann-Gibbs principle later, but this was introduced by Hermann Rost already a long time ago to discuss equilibrium linear fluctuation problem. Then I think in the 80s, there are many studies, but they are most just model-dependent studies. Then I think Joseph Fritz introduced a resolvent approach, which is a rather general approach. And but I think this is already forgotten. But he discussed the Ginzburg-Landau lattice model, and next year, Guo Papanicolaou Baladan introduced now it is called the entropy method, taking this Ginzburg-Landau model as their model. And we will discuss this method later. And also, slightly after, so as a variant of the entropy method, H.T. Yao introduced a relative entropy method, which also I will discuss later, this relative entropy method. And for the non-gradient case, Baladan introduced the method gradient replacement in 94. And then Kip Nisrandi's book appeared. And also, I just mentioned this Otto and Villani and others introduced the method to solve the hydrodynamic limit, the method of the optimal transportations. I think this is almost forgotten by now, but maybe there is some chance to extend the result. I still believe this is useful. So this gives a very short history. I miss many important literatures, but just give a short history of the study of the hydrodynamic limit in probability group. And this meeting is also the main theme is fractional equations. And yeah, we are very happy that yesterday there's a talk by Bernard Dunn and also Hannes talk. They gave a very nice talk to derive some fractional equations, say in the Cedric case with the boundary conditions depending on some parameters. And yeah, anyway, due to the hydrodynamic limit, we can derive by this result, we can derive some fractional equations. Just I want to remind you, yesterday very nice 2 talks. Then I want to give an essence, the method to prove the hydrodynamic limit due to the Guo-Papanicolaou-Baladan and also Yau's relative entropy method. A very quick review how to derive the local equilibrium situation and also local ergodicity. And okay, the Guo-Papanicolaou-Baladan consider the entropy, relative entropy. So let mu t n, so n is a scaling parameter, and this is a microscopic distribution. So we have a microscopic system, and we usually consider some diffusive or maybe also hyperbolic, but some scaling in time. So this t is already a macroscopic time, but we still keep the microscopic system at time t. So this is a microscopic measure, but at a macroscopic time t. Then we consider the relative entropy of this real system with respect to nu, which is one fixed equilibrium state. Then just take its time derivative. Then you see that this is bounded by minus constant times n square. N square comes from the time change times the Dirichlet form of the square root of this is the Radon-Nikodym derivative of this real system, the measure of the real system at time t with respect to the equilibrium measure nu, and we take a square root. This is sometimes called the information, but by a simple computation, you obtain this kind of estimate. Then you integrate both sides in t from 0 to capital T. Then Dirichlet form is actually convex in mu. Therefore, the time average, we don't divide by t, but roughly time average of the real system, that Dirichlet form is bounded by this object, entropy at the 0 minus entropy at t. And then entropy behaves like a volume order. So anyway, we divide by the volume. Then since we have this vanishing factor, the Dirichlet form of the time average of the mu t n per volume goes to 0, by this very simple argument. And then so in the limit, this Dirichlet form vanishes. And that already implies the measure, the limit measure is a combination or the superposition of the equilibrium states. And like Maxwellian distributions or the Poisson distributions, we have a family of the invariant measures or the equilibrium measures. But this very simple argument implies the limit of the time average of the real system is a superposition of the equilibrium states. In the independence case, you already see this is a superposition of the Poisson random field. And this is already, we show already the local equilibrium. And by using this fact local ergodicity, that is averaging effect under this equilibrium states. Also, we can realize by showing the so-called one block and two block estimates. This was done by Glauber-Kawasaki. So roughly saying they use entropy as a Lyapunov function, and the Lyapunov function goes to 0, implies also the Dirichlet form goes to 0, implies the local equilibrium. That is just essence of the idea of the proof of the hydrodynamic limit. Okay, just for the gradient system. And the relative entropy method, which was introduced by the H.T. Yao, he considered the relative entropy not one fixed equilibrium state, but he took some so-called local equilibrium, and then he just compared the real system with respect to the this local equilibrium. But we have to define the local equilibrium. And yeah, but later I will discuss this method more precisely. Then maybe how to, the point is how to choose this local equilibrium, but I will explain later. So this is the essence of the entropy method. Okay, I hope this gives us some introductions. And then now I want to move to the topics which I want to talk today. So today I want to talk about the derivation of the motion by mean curvature from some microscopic system. The model we take just random walks, but not independent, but interacting random walks. And also this system has a creation and annihilation of the particles. So we consider two types of the microscopic system, and the creation annihilation mechanism is called the Glauber dynamics, and the one is a zero range process. The other one is the Kawasaki dynamics with speed change. The Kawasaki dynamics is sometimes called the exclusion process, and therefore these are the hardcore interactions. But the zero range process doesn't have this kind of hardcore interaction, just random walk moves. But in this case, random walk have some interaction at the same sites. I wrote here. The range case, random walk have interaction at the same site. On the other hand, Kawasaki speed change means the random walk with the exclusion rule. That is a hard rod interaction, and also it has a finite range interaction. That is called the speed change. And the Glauber part, as I said, the creation and annihilation particles interactions. So this has also the finite range interactions. And we consider on the d-dimensional discrete and the periodic d-dimensional periodic lattice of large size n. And each particle jumps to the neighboring sites. No, we don't consider the long heavy-tailed jump, but only to the neighboring sites. Okay, so then our goal is derivation of the interface motion, especially the motion by mean curvature, directly from the microscopic system. The proof is the combination of the probabilistic part. We actually use the relative entropy method due to H.T. Yao, and we combine it the Boltzmann-Gibbs principle. And in the PD part, we have to control some the solution of some hydrodynamic equation. Then we show that discrete Schauder estimate and also Nash the estimate is useful. Yeah, we use. And also finally, we use the sharp interface limit for the discrete actually nonlinear Allen-Cahn equation appears. But the discrete nonlinear Allen-Cahn equation, we show the sharp interface limit by using the expansion up to the second order. And this is so-called the second order is so-called the corrector in the homogenization theory. So it's a combination of the hydrodynamic limit and also the homogenization. And we use the comparison type theorem for the discrete PDs. And this expansion is something like Hilbert expansion or the Chapman-Enskog expansions. So there is some similarity. And we discuss only the zero range case, not the Kawasaki case. So we only discuss the zero range case and not, finally, I give some small comment on the Kawasaki case. Okay, let us formulate the problem more mathematically. So let us explain the Glauber-Zero range process. The particles move on the, as I said, on the discrete d-dimensional torus, the side length capital N. And the particle number at the site x is taken from this lattice. At the particles number at the x is denoted by eta x. So the process which we consider is the correction of the eta x at the time t, and depending on the scaling parameter n, but this is the correction of the particle number over the this discrete torus, which I denote eta nt. And this is a Markov process, taking the value in the configuration space. The configuration space is this is a collection of the particle numbers at x. Therefore, particle numbers takes z plus. The particle number is non-negative integers at the discrete torus. Therefore, the eta nt is a Markov process living on this xn, the space xn, which is called the configuration space. In the Kawasaki case, the particle number is 0 or 1. Therefore, Kawasaki case xn is a 0, 1 to the power tnd. So, and this Markov process has a generator given by this form. We call Ln(k), which is the sum of the zero range part and the Glauber part. And the zero range part, and the generator is given by Lz. And the Glauber part, the generator is given by Lg. And for the zero range part, we have this, the generator has this form. And some function g. G is a function defined on z plus. So that only at a single site, we look at how many particles stays at the position x, and we give some interaction is given by g. So the speed of the jump is governed by this function g, and this means that the jump. So we have a eta from this configuration space, and then after some transition happens from one particle at x jumps to x plus e, and e is a neighboring site. So x plus e is a neighboring site because e is taken actually from the integers vector, and with one coordinate is +1 or -1. The other one are all other coordinates are 0. So this means from x to the neighboring side, x plus e at the one particle jumps. So maybe eta xy means eta after one particle jumps from the side x to y. So this is a new configuration after one particle jumps from x to y. So G0 should be 0 because if there is no particle, nothing happens. Therefore, G0 should be 0. And this is gives the interaction, in fact. And for the Glauber part, this is a creation. This governs the creation and annihilation of the particles. And this is the sum of the plus and minus. And this means plus means okay, eta x plus means from eta one particle is created at the position x, and eta x minus means eta from eta one particle is annihilated at this position x. So creation rate is given by cx at the position x is given by cx plus eta, and annihilation rate is given by cx minus eta. Okay, so I hope this explains the mechanism. And also we introduce the time change, n square diffusive scaling for the zero range part. So if g eta x is just a linear function, eta x, then zero range process is nothing but independent random walks. So something like independent, but some interaction comes in from this factor. Then we introduce diffusive scaling in the for the zero range random walk part. And for the Glauber part, we fix and we introduce some other scaling k. At the moment, k is fixed, but later we change k depending on n, but just slower than n, much slower than n. Okay, so this, I hope this explains the mechanism of the time evolution of the random walks with creation annihilation particles on the discrete torus on the side length n, the d-dimensional. Okay. And G I explained already, and this is the independent case is equivalent, and we assume some conditions on G, actually linear growth and spectral gap, but I just skip it. Then it is known that invariant measure is very important, as I explained at the beginning. This is the equilibrium states. And the independent case, it was just a product of the Poisson distributions. But because of this interaction, this becomes a generalized Poisson distribution. But invariant measure, actually the product measure on the if the sites are different, then the invariant measure is actually independent. So what is the generalized Poisson distribution? That is given by this one. But this has a one parameter family we call phi. So invariant measure is not unique. And it is parameterized by some parameter we call phi. And once phi is given, then we define the measure on the one side by this form. So in the Poisson case, this should be the k factorial, but we change it by gk factorial. Gk factorial means the product of the, so this is a gk, sorry, maybe I didn't write, but this is just gk times gk minus 1 times g1. This is the product of gk. Then we normalize it to be the probability measure. Then we take a product for the on the lattice, but instead of the parameter phi, we introduce another. We can change the parameter to the density. So instead of phi, we use rho as its parameter by changing by this formula. So this means we have this measure, but this is the average of the particle number. Therefore, rho is the mean density of the particles. So we can change the parameter from phi to rho by this relation. And the phi is certainly the function of rho. And we also have phi at the average of the expectation of the gk. So under this measure, mu rho, if you take expectation of g, you can recover phi. And that is very easy from this formula. Okay, so this is the invariant measure. So I explained the zero range part, and this is the invariant measure of the zero range part. Okay, the Kawasaki part, sorry, the Glauber part moves much slower. Therefore, Glauber-Zero range, actually this invariant measure plays a role, essential role, because Glauber part is much slower. In the Glauber part, we assume the something, but this is shift invariant, and we will choose some in the special form, but I don't touch here. Okay, but certainly gx minus z, if a particle number at the x is 0, then annihilation rate should be 0. I don't write, but it should be okay. Then the scaling from the microscopic to macroscopic. This is what I wrote at the beginning. It's the same as before. So we introduce a macroscopic empirical measure, which is a density of the particles from the macroscopic viewpoint. Therefore, the spatial space is actually scaled down. Originally, we have a microscopic space, which is a side length is capital N, which is very large. But macroscopically, the side length becomes 1. Therefore, the macroscopic space becomes just a continuous torus, or the unit, just unit cube in 3D case, but unit cube under the periodic boundary condition. And a macroscopic empirical measure is defined by this formula. So what is this? So we squeeze the space by dividing by n, like this. And we put the mass at this point, eta x. So originally it has one particle has a mass 1, but we divide by n to the power d. So one particle has a mass 1 over n to the power d. So macroscopically, originally one particle had the mass 1, but macroscopically mass becomes very small. And we introduce the time change m squared, and for the Glauber part k. So this scaling, we don't introduce the time change here, but spatially we squeeze by n, and the mass is also becomes very small. And but in the dynamics, we introduce the time change like this one. Okay, so we are interested in the limit of this macroscopic empirical measure. So first, I want to discuss the hydrodynamic limit for fixed k. So generator was given by this one. The zero range part is speeded up, and the Glauber part is not, but the k is fixed. So then we can prove that so in eta we take the process eta and t generated by this one. So for eta in the last slide here, eta, we take eta tn. Then this is random object because this is a random time evolution. But in the limit, we can prove that this converges to law, actually in probability sense. And this is a deterministic object, and this satisfies this nonlinear Allen-Cahn equation, which is a kind of reaction diffusion equation. And what is phi and what is f? Phi is the average of the jump rate of the zero range part under the equilibrium measure new law. This is generalized Poisson, the product of the generalized Poisson distribution. So roughly saying, system reaches the equilibrium state for each position. So position is the macroscopic position is denoted by v, because x is used for microscopic. So we denote by v for the macroscopic spatial variables. Then for each t and v, it reaches the equilibrium. Therefore, in a sense, by local ergodicity, we take an average of this jump rate. So that comes here. And from the Glauber part, we have a creation and annihilation. But again, we take an average of the this equilibrium measure due to the ergodicity, local ergodicity. And we get the f, which is this creation rate give a positive effect for the density law under the time derivative. This increase if the particle increase created. If annihilated, the particle number goes down. Therefore, it gives a negative effect. And then we take an average. So this is this is a macroscopic equation derived by the hydrodynamic limit. I don't give a precise proof, but we can use the entropy method or relative entropy method, which I explained at the beginning. And but this is a low large number. So this is random object, but this is deterministic object. yeah, if initial value is given. Okay, so we are interested in the balanced case. Actually, we want to derive the motion binding curvature directly from the particle systems. Then actually it is known from this, actually not known, but in the linear, at least the linear case, if phi is a linear function, then this is called the Allen-Cahn equation. And since phi is a nonlinear function, we call it the nonlinear Allen-Cahn equation. Then at least when this is linear, it is known that if f satisfies balance condition, then f is bistable and it satisfies the balance condition. Then we can derive, when k goes to infinity, we can derive motion binding curvature, which I want to explain. So first, we choose the creation and annihilation rate in the following way. First, we can construct, I don't give precisely, but we can construct the creation and annihilation rate C plus minus eta in the following way. The corresponding f, which is the average of this one, is bistable. Bistable means the f has exactly 3 zeros, like this figure, alpha 1 and alpha 2, and in between alpha star. And at the alpha 1, the derivative is negative. So this direction and the slope is this direction, and but alpha star, it is a positive derivative. And this means this is called the so-called the bistable, because if you consider the ODE part, so if you neglect the diffusion part, this is just ODE. And if f is positive, then the rho increase. And if it's negative, then the rho decrease. Here, f is positive. Therefore, for the OD part, the drift goes to the direction to the alpha 1. Here, f is negative. Therefore, for the ODE, drift goes to the direction to the alpha 1. In this sense, alpha 1 is stable. And it's the same for alpha 2. But alpha star is unstable. Starting from the neighborhood of alpha star, then it goes to alpha 1, alpha 2, or alpha 1. Therefore, alpha star is unstable. So this is called a bistable because it has two stable points, two stable solutions. And especially when f satisfies this relation, this is so-called the phi balance condition. That is, we can construct a potential W, which is associated with this F, and also it depends on phi this way. So once this is satisfied, the potential has certainly two bottoms because due to this one, but by balance condition, its height is the same, or the level, the strength of the two bottoms are the same. That is the phi balance condition. So one can derive the homogenized motion by mean curvature starting from a nonlinear Allen-Cahn equation 1. So this is discussed in our paper. I think it was not only linear case was discussed, but we can discuss also the nonlinear case, nonlinear diffusion case. But anyway, our goal is not discussing this equation, but discussing the particle system. Okay, then from microscopic level, what does it mean? So microscopically, we have two different phases. One is a sparse region. The other, so roughly saying the density is alpha 1. So in this picture, outside is a very sparse area. The average density of the particle is alpha 1, and inside is a dense area. This is the average density is alpha 2. So microscopically, the particle system is in a sense separated in the dense area and the sparse area. And if you observe it, the macroscopic viewpoint, just you squeeze by n, then you have a dense area and the sparse area. which is separated macroscopically by some interface we call gamma t. And we want to prove how the evolution of gamma t is given. Actually, under the balance condition, we can prove gamma t evolves under the motion by mean curvature, but with some homogenized effect. So this is the main result, our main result. Let's consider the eta and t governed by this one. Now, k also move in the hydrodynamic limit we discussed in the last section. K was fixed, but now we move k together with n. Then, as before, we consider the macroscopic empirical measure. Then the main theorem is this one. So we assume these greater than or equal to 2, and assume that all conditions which we didn't write very carefully, and some initial some condition for the initial distribution in the next page. And k goes to infinity actually, but we need some bound, upper bound. Okay, n is bounded by delta 0 times log n, rather slowly, and to the power sigma divided by 2. And sigma is some constant which appears by the Nash estimate, but and also delta 0 should be small. So anyway, k goes to infinity, but rather slowly. Then we can prove the macroscopic empirical measure at the time t converges to chi, what we call chi gamma t. This is the step function. Actually, we need the density dV, but we don't write that carefully. So chi gamma t is a step function, and on the one side of gamma t, so there is some interface of the hypersurface appears, and one side of the gamma t, it takes a value alpha 1, and on the other side, it takes a value alpha 2. So chi is a step function macroscopically. As I said here, just the value should be in the average. So in the microscopically, it's quite random, but in the average, the density should be alpha 2. On the outside, it should be alpha 1. So the limit should be the step function taking value alpha 1 or alpha 2. So we can prove this situation, and hypersurface gamma t, which separate alpha 1 and alpha 2, evolves under the homogenized motion by mean curvature. That we mean the v. V is the normal velocity of gamma t from alpha 1 side to alpha 2 side. That is given by the product of lambda 0 times kappa. Kappa is essentially the mean curvature.
Can I call you back?
Okay. So d minus 1. So this is the sum of the principal curvatures. Then the lambda 0 is given in the next page, and sigma to the local equilibrium. Yeah, of course, if mu 0 n is equal to this, then it is satisfied. But independence, so we assume independence. But this under this condition, we can generalize. And also we assume this is U0 has enough regularity. And also at time 0, we define the initial interface gamma 0 as a level set of the U0 with the value alpha star. Alpha star is just the unstable point of F. So this means that inside or outside of gamma 0, the value is bigger than alpha star, and on the other hand, on the opposite side, the value of the U0 is smaller than alpha star. So yeah, in this way, the gamma 0 is just separate two stable values, alpha 1 and alpha 2. We assume the enough regularity for this gamma 0 also. Okay, so this is the assumption for the initial values. And also, okay, so so this is the assumption for the initial distribution. And I have to explain what is the lambda 0. This comes from the homogenization effect. And physically, it is interpreted as a product of the surface tension and the mobility. And it is given by this formula. But maybe I cannot explain the details. But at least when phi is linear, function, then the lambda 0 is 1. Then there is no such effect. But we have some explicit formula. This comes from the second expansion in the like a Chapman n-scope expansions. But anyway, corrector from the corrector, we can get this formula. Okay, so the unbalanced case we don't discuss yet, but we have the time change should be the different. We should have a much shorter time scale. Then we expect that the limit dynamics is not the motion by curvature, but the Huygens principle. It was a long time ago discussed by this kind of sharp interface limit was discussed at the PD level by Jürgen Gelton for the linear case. So we expect something different for the unbalanced case. So I can show you some simulation result due to Yoshiki Otobe. So I can show you some just for fun. Sorry. I can show you, this is a 200 times 200. Then we run actually this is Kawasaki case. So 0, 1 value. So just with the exclusion rule. So, and also Glauber. Yellow part is no particle, and the blue part, there is at least one particle. So this is 200 times 200 grid. So we don't see much, but you have some image. There's some, you can feel something. And another one, maybe. This has a grid 1,000 times 1,000, much more sharp. It's not okay. So it doesn't. It is fit. Sorry. Okay. So this is 1,000 times 1,000. It's slow. Sorry. Maybe it's better to finish. I think it's consumed. I think so. Anyway, come back to the slides. Okay, so I have 10 minutes. So finally, I want to give some feeling for the proof. So as I said, it consists of two parts. One is the probabilistic part. The other one is the more PD part.
Sorry, actually, there should be 5 minutes because we also want time.
Okay, sorry. Okay. So 5 minutes. Okay, I understand. Okay. So we use the relative entropy method. Relative entropy, we consider some first, we define the local equilibrium that is a product of the generalized Poisson measure. And then the average is chosen according to this discrete hydrodynamic equation, which is a discrete Allen-Cahn equation. Okay, then by choosing the local equilibrium with the mean given by this equation, the solution of this equation, we can prove the real system, the relative entropy of the real system with respect to this local equilibrium behaves like a small o of the volume. And some assumption, this one. And this can be, once this is shown, then we can show that this macroscopic empirical measure is very close to the solution of the discrete hydrodynamic equation by using entropy inequality and also some large deviation type estimate. This is rather standard. And once we can prove in the PD part, this the solution of the discrete hydrodynamic equation, that is the discrete Allen-Cahn equation, converges to the motion by mean curvature like this, then the proof of the theorem one, main theorem, is done, completed. So we have to prove this one first, and then we use the relative entropy method due to Yau. So we take a time derivative of this relative entropy. Then we have some formula, but we have actually that Dirichlet form. But in this argument, we just neglect. This is negative effect. We just neglect, and then we have some messy formulas. But we can estimate the right-hand side using the relative entropy itself again, if we choose a local equilibrium in the proper way, as I explained. And we give some computation like this, but here some nonlinear function appears. We have to replace this by the linear function. For that purpose, we use we need a Boltzmann-Gibbs principle. And also some factor comes here in front of this, in front of the replacement factor. Then first I explained the Boltzmann-Gibbs principle. This principle roughly saying that we have some messy term, a messy microscopic function. Then this can be replaced by its average, but with the mean given by the solution of the discrete hydrodynamic equation. And the next of the term is like a Taylor expansion. You have a derivative and linear term. So you can, so you want to replace h by this term. So so the capital F is the difference of these two terms. And then this is, and there's some prefactor A. In this case, this factor is here. So we have some estimate, and this is essentially estimated by entropy itself. But if we choose, it is important, if we choose U as the solution of the discrete hydrodynamic equation. And also to control this prefactor A, or this term, this is the second derivative of the solution of the discrete hydrodynamic equation. We prepare the Schauder estimate for quasi-linear discrete PDEs. I think this is also interesting itself, but I don't have time. The Schauder estimate, we use something well-known approach in the PD theory. And one is a Nash-Held estimate. Then we prove the Schauder estimate. In the discrete setting, Strick and Sen proved some Held estimate. Then by using Held estimate, we can go to improve the regularity and go to the Schauder estimate. Okay, I don't have time. So then replacing everything by the linear term, summarizing, we have actually this term. But if we choose this U as the solution of the hydrodynamic equation, this goes away. That is the point. Then we have this estimate, then by the Gromwall, and then we have the proof of the one. Then we prove the shampoo interface limit for the solution of the discrete hydrodynamic equation, but we essentially use a comparison theorem for the discrete PD and also generation of the interface at the short time interface reaches some okay, and also propagation interface. So sorry, I don't have that time. So maybe I should stop here. Thank you very much for your attention.
So I will first take questions from the audience here, and then if the online participants have questions, please use the raise your hand option, and then we'll come to you after the questions here have been taken. So are there any questions here in the live audience? Yeah. Yes, sir.
Thank you. A member of Cambridge Statistical Laboratory, Frank Kelly became famous for studying a special type of zero-range process, the so-called Jackson and Kelly networks, as models of computer systems. However, his book doesn't contain any equation of Allen-Cahn type. The question is, what could be said about the applications of Allen-Cahn equations to computer science?
Sorry, I don't know anything about the computer science, so I have no idea to your question. Sorry.
Any more questions here? Are there online questions? Okay.
Hello, Enrico, can you please unmute your mic?
Yes, so can you hear me?
Yes, we
Yes.
can.
Yes, so thank you very much for this very interesting talk, especially very difficult problem of studying the motion of interfaces. And in fact, I wanted to ask you what is known about the motion of interfaces, for instance, in the Ising model. I mean, if you know something, or if there is any, from the rigorous point of view. Of course, there are a lot of papers by physicists using Monte Carlo simulations, and other approximate tools. But if there is, if you are aware of any progress in terms of rigorous results, as in your case.
So I don't know, but in the Kawasaki case, is the 0, 1 value. So it's something like a Ising model, but a dynamical Ising model. So Kawasaki is, you can interpret this model as a Ising model, the time evolution of the Ising system. With sometimes it the number of the 1 and the number of 0 is preserved. That is Kawasaki part. But the Glauber part anyway destroyed this conservation law. So we consider something like such kind of Ising time evolutions. I think we can say in that way also. But the range is not. But we also studied the Kawasaki case. So I hope it, and also there are several other things studied by Herbert Spohn and also say Italian group at the corner of the Ising corner. They derived some interface motion. So there are several related studies. That is true.
Thank you very much. Thank you very much.
I do not see any raised hands from the virtual participants. If there are any questions, you may please unmute your mic.
Okay, if there are no more questions, then let's thank the speaker again.
Thank you very much. I don't know how to.